Yes, thank you. It's a pleasure to give a talk here at the 7th SwissMap meeting. And as advertised by the title, I will be talking about advances in integrable deformations of superstrings. And the outline of the talk is the following. So I will start with a gentle introduction on integrability. Then I will focus on one special type of integrable model, which is the ETH deformation. And then I will discuss the recent advances in this field by looking at one specific example, namely the ETH deformed ADS5 cross S5 superstring. And I will end with some conclusion and also mention important open problems that still need to be solved. So let's start with an introduction on integrability. So integrability, loosely speaking, you can think of it as being the presence of enough conserved charges so that the dynamics of the system is constrained and you can come up with methods in order to solve the theory exactly. So this integrability is most precisely formulated in the context of classical mechanics. So if you have a Hamiltonian system with n degrees of freedom, then this system is called Liouville integrable if you can find n independent conserved quantities that are in involution. Involution means that the Poisson bracket of these conserved quantities vanishes. And Liouville integrability, so if these properties are satisfied, then you can solve the theory exactly. So you can go to what is called angle action coordinates, and this will allow you to solve the theory exactly, meaning that you can express the solution in terms of integrals. So this is said, it's said that you can solve the theory by quadratures. Another important formulation of integrability for classical systems is the notion of Lax-Baer formulation, and this is very useful in order to actually find these conserved quantities that characterize your integrable theory. So the Lax-Baer is a pair of matrices L and M, and if it is possible to rewrite the equations of motion of your theory in terms of this type of equation, where here the bracket means that you take the commutator between the two matrices, and M and L have entries that actually depends on the phase space variables. So if you can rewrite the equations of motion in terms of this type of equation, then your theory is integrable, and you can obtain the conserved charges by taking the trace of powers of this matrix L. So this is for classical mechanics. So what about integrability for field theories? So the problem here is that field theories have infinitely many degrees of freedom, and you cannot, so the Liouville integrability cannot be readily extended to this case. However, for two-dimensional field theories, there is something that saves you, namely the Lax-Baer formalism that I have just introduced admits a natural generalization. So for one dimension, so for classical mechanics, we have seen that integrability can be recast as this equivalence between equation of motion and this equation for the Lax-Baer. And the two-dimensional field theories, if you can rewrite the equations of motion as the flatness condition for a connection L, which generalizes this L and M that you have for one dimensions, then you can call your theory classically integrable. So here it is one-dimensional because you only have time, and here it is two-dimensional because you have time and some other, or just two variables. So this is for classical field theories, and now you can also ask what happens for quantum field theories. So what about two-dimensional quantum field theories? Well, this type of theory, you can expect the quantum system to be integrable if the underlying classical theory is integrable and if the conserved quantities actually survive quantization. And this condition imposes serious constraints on the scattering matrix of the theory. So the scattering matrix encodes the probability of having some scattering process. So what are these constraints that are imposed on the S matrix because of integrability? So the first condition is that you don't have any particle production, meaning that the number of incoming particles should be the same as the number of outgoing particles. The second condition is that the set of incoming momenta is the same as the set of outgoing momenta, meaning that what happens is that the momenta are just reshuffled among the particles. And the last condition is that you have factorization of the S matrix. So if you have an n body scattering, then it can be decomposed into a sequence of two body scatterings. And this last condition actually gives rise to an equation for the two-body S matrix. To see this, let us consider the case of the scattering of three particles that I label 1, 2, and 3. Now, because you have factorization, this can be rewritten in a sequence of two-body scatterings, and you can actually do this in two different ways, depending which particles scatter first with each other. So either 1 and 2 or 2 and 3. And compatibility requires that the result you get from doing this computation or this computation should be the same. And this gives rise to a condition on the two-body S matrix. So this is this equality, and this is the quantum Yang-Baxter equation. So the quantum Yang-Baxter equation characterizes is necessary for your quantum theory to be integrable. So why am I talking about two-dimensional integrable quantum field theories? So because this is actually relevant also in the context of string theory. So in string theory, what happens is that instead of having particles, your fundamental building blocks are strings, so one-dimensional extended objects, so that, for instance, you can take to be closed. And then the string theory, so and this string, as time evolves, will sweep out the two-dimensional surface in target space, so in space-time, and this is the world sheet. And you can think of string theory as being a special type of two-dimensional field theory, so a two-dimensional sigma model, meaning that it is a theory for fields that are actually maps from the two-dimensional world sheet to the target space. And in string theory, in superstring theories, this target space is actually 10-dimensional because of math. So you can see string theory as a special type of two-dimensional field theory, so that what I've discussed about two-dimensional quantum field theories or two-dimensional classical field theories also applies in this setup. So because for some target spaces or some spacetimes, this theory will actually be two-dimensional integrable. So it will be classically integrable in the sense that you can find a Lax, you can reformulate the equations of motion in terms of the flatness condition for a Lax connection. This is in particular the case for the ADS5 cross S5 superstring. So the ADS5, so where the target space is the product between a 5-dimensional anti-de Sitter space and the 5-dimensional sphere. So this type of theory is classically integrable. Furthermore, the exact S matrix, assuming that the integrability still holds also at the quantum level, can be bootstrapped using the symmetries of this theory. And this is particularly interesting because from this exact two-body S matrix, you can then actually deduce physical observables in target space, such as the string spectrum. So by computing the two-body exact S matrix on the world sheet using integrability techniques, you can obtain the string energy spectrum. And this type of geometry, ADS5 cross S5, is also particularly interesting in the context of ADS-CFT holography, where so this is a duality between string theories on anti-de Sitter space and conformal field theories living in one dimension less. And one celebrated example of this ADS-CFT duality is the correspondence between strings on ADS5 cross S5, so on this geometry that we just saw, and on the CFT side we have n equal 4 super Young mills in 4 dimensions. So this is also one of the reasons why studying this type of geometries is interesting, but in this talk I will not go into the details of this duality, but I will mainly discuss integrability of the ADS5 cross S5 superstring. So I have mentioned that integrability techniques can be used in order to obtain physical observables in this setting of ADS5 cross S5. And now you could wonder whether it's possible to apply or to also do all these steps in the case where you have less supersymmetries. So when you deform ADS5 cross S5, and this actually turns out to be possible. So you can obtain other integrable theories with less supersymmetries, but whose exact S matrix can also be computed exactly. And one specific example are the integrable ETH deformations. So now I come to the second part of the talk where I present the features of these ETH deformations. So the ETH deformations, they will deform the space-time in which the strings propagate. So instead of having ADS5 cross S5, you will have deformed ADS5 cross S5. So you can see this for the sphere. If you take the two-dimensional sphere and apply an ETH deformation, you will end up with a squashed structure. The action has two new ingredients with respect to the undeformed theory. So one is a real parameter eta, that it controls the strength of the deformation, and eta equal to 0 gives back the undeformed theory. So these ETH deformations, the name comes from this parameter eta, and furthermore, there are continuous deformations of the ADS5 cross S5 superstring. The other ingredient that is the one that controls the shape of the deformation, and this is a Drinfeld-Jimbo operator. So what is that? So this is a linear map from G to G, where G is the symmetry algebra of the undeformed theory. So later on in this talk, we will see what this symmetry algebra is in the context of ADS5 cross S5 superstrings. So once you have this Lie algebra symmetry of the undeformed theory, you can decompose it into a set of Cartan elements, positive and negative roots. So you choose a particular Cartan Weyl basis, and the Drinfeld-Jimbo R matrix will annihilate the Cartan elements and multiply with plus and minus I the positive and negative roots. So those are the two new ingredients in the deformed theory. And by construction, this deformed theory will be classically integrable. So again, you can write down the equations of motion in terms of a flatness condition. Yes?
Sorry, so I'm used to R matrix, which is a map from G tensor G to G tensor G. So how they are related?
Yes, yes. So there is indeed a relation between this R matrix and the one that goes from G tensor G. And if you work in terms of super matrix realization, this is with the super trace.
Ah, this is the trace in some sense of the other one.
Yes, yes.
Okay, interesting. I didn't know it would take trace. It's infinite dimensional. Okay.
But this is a classical R matrix, right?
Yeah, this is a classical R matrix indeed.
Okay.
But even the classical R matrix, you can write it into different ways.
And the deformation, are you deforming the two spaces? Are they deformed separately? The deformation space is still like a product of...
Yes, the deformation space is still a product. Well, there is a subtlety when you consider the full background. But if you just consider the geometry, what you see, then it is still a product. But then when you include fermions, you have other ingredients that appear. You have this Ramon-Ramon fluxes. And for some of these ETH deformations, what will happen is that you will actually mix the two adjacent sphere. But this is a subtlety, and in general, they are separated. You separate them, you deform them separately. This is classically integrable. The equations of motion can be rewritten as a flatness condition for a lax connection, and the manifest symmetry algebra is no longer there in the deformed theory, so it is broken down to the Cartan subalgebra. However, there are hidden symmetries, and in the case of ETH deformations, these hidden symmetries correspond to a Drinfeld type quantum group. So now, maybe for the pleasure of the mathematicians in the room, I will say a few words about this Drinfeld type quantum group. So remember that Lie algebras are rather rigid objects and you cannot deform them. And the trick of quantum groups is to consider a larger structure, maybe the Hopf algebra, which you can think of as being a Lie algebra with an additional structure, in particular the coproduct, which is a Lie algebra homomorphism. So this is the coproduct, is delta. And so this Drinfeld quantum group will actually be a deformation of the, will be a Hopf algebra itself and will be a deformation of the original Hopf algebra. So let me maybe give some formula to explain this. So let us take a Lie algebra whose commutation relation. So here I notice I use E and F for positive and negative roots. Before it was E plus and E minus, but it's the same. So the commutation relations are dictated by the Cartan matrix A. And when you do, so the Drinfeld quantum group will be the same, except that for the commutation relation between positive and negative root, you will have a different factor. So there will be this parameter Q appearing. Q is a complex number. And when you take Q going back to 1, then you obtain again the original Lie algebra. So this is at the level of the commutation relations. So let's also look what happens at the level of the coproduct that I have mentioned. So for the Lie algebra, the coproduct is trivial. However, this is no longer the case for the quantum group. So there is this parameter Q that also appears in the coproduct of the positive and negative roots. And again, if you take Q going to 1, you recover the original Lie algebra. So Q is a complex number. However, the representation theory is rather different whether you take Q being a phase or Q being real. And in fact, the ETH deformations that I have been mentioning, they correspond to Q being a real number. And this is this Q will actually be related to the deformation parameter eta of the ETH deformation. But there exist, as a side remark, there exist also Q deformations with Q being a phase, and these are called the lambda deformations. So these are the symmetries of the, or the conjectured symmetries of the ETH deformations. However, when you consider ETH deformations of superstrings, you have a subtlety because you actually consider quantum groups or quantum supergroups because you have G is a superalgebra. And we have, as maybe you have noticed, both the Drinfeld R matrix that appears in the ETH deformation, as well as the definition of the quantum group that I have given here, they depend on the choice of a Cartan-Weyl basis. So a choice of H, E, and F. And in the context of superalgebras, you can actually have different types of you can have inequivalent Cartan-Weyl bases. So to illustrate this, let us take the example of SL2/2, this superalgebra, which you can think of as being the set of 4x4 supermatrices with vanishing supertrace. So the supertrace is defined as the trace of this 2x2 block minus the trace of this 2x2 block. So the blocks in blue are the bosonic generators, and the out of diagonal elements are the fermionic generators. Now, if you consider matrices, it's customary to take the Cartan elements to lie on the diagonal, the positive roots to lie in the upper triangular block, and the negative roots to lie on the lower triangular block. And this actually corresponds to choosing the simple roots just above the diagonal. And the thinking diagram corresponding to this choice of Cartan-Weyl basis is the following. So the circle, the empty circle is a bosonic simple root, and the circle with a cross is a fermionic simple root. So this one corresponds to that simple root, this one to that one, and this one to that one. This is the distinguished thinking diagram. It is called distinguished because it has the maximal number of bosonic simple roots, and it actually contains the bosonic algebra as a subalgebra. So this SL2 and this SL2. However, this is actually not the only choice, and SL2/2 admits two further thinking diagrams with increasing number of fermionic simple roots. So this one is the one with all three fermionic simple roots, and this one has two fermionic simple roots and one bosonic simple root. So we have these different thinking diagrams, and well, we would like to understand how they will affect the quantum deformation, so the quantum group that you construct. So for this, let me consider two different Cartan-Weyl bases. So Cartan-Weyl basis number one and the other one, where all the quantities will be denoted with a prime. What happens is that the associative algebras are isomorphic, so you can find this Lie algebra homomorphism, omega, that goes from one Cartan-Weyl basis to the other. However, the coproducts are related by a twist. So there is this operator F here that relates the coproduct when you choose this type of this Cartan-Weyl basis and the coproduct delta prime corresponding to this Cartan-Weyl basis. So the quantum groups are not equivalent, or they are a priori not equivalent because they are related by this twist. And as a physicist, you may wonder what the physical implications of this twist are on your ETH deformation, on your model. So one question that you can ask is whether the ETH deformation that you construct is actually a string theory, and whether the twist will affect whether you have a string theory or not. And another question you can ask is whether the physical quantities that you compute are actually affected by the presence of this twist. And I will now answer those questions in the context of 5 superstrings. So I consider ETH deformations of ADS5 cross S5 superstring, but maybe there are some questions before. If not, so let's consider this setup of the ADS5 cross S5 superstring. So the symmetry of the undeformed theory, so let's analyze the symmetry of the undeformed theory. So both the ADS5 and S5 are symmetric spaces, meaning that you can write them as their coset manifolds. And when you add supersymmetry on top, you end up with a super coset, so namely a semi-symmetric space, and the isometry algebra is this PSU2, or the, yeah, so this is the supergroup, but you also have, of course, the super algebra, PSU2,2/4. So this is the undeformed symmetry algebra that you will then Q-deform when you want to get the ETH deformation. So PSU2,2/4 has many inequivalent Cartan-Weyl bases that are characterized by the different thinking diagrams. So you have many different possibilities, among which the distinguished thinking diagram that we already encountered before, because it has the maximal number of bosonic simple roots, and you also have, in this case, you have the fully fermionic thinking diagram, and then you have many other thinking diagrams. And the question you can ask then is, Well, what happens if you construct your ETH deformation using these different types of thinking diagrams? Will you get the same theory? Will they all be string theories? And so on. So let's ask the question of what happens to their string theory interpretation. As it turns out, there is only one choice that gives you a valid string theory, and this is when you choose the Drinfeld R matrix to, or your Cartan Weyl basis to correspond to the fully fermionic thinking diagram. The others are not string theories, so for the expert in the room, they are actually solutions of generalized. There are some solutions of generalized supergravity, but I don't want to go into the details here. And here, I just want to highlight that only the fully fermionic thinking diagram gives rise to a supergravity background, so a string theory. The other question that one can ask is what happens to the exact S matrix, because this is really the ingredient that will give you the physical quantities. So the S matrix I mentioned when I was talking about integrability, I mentioned that it can be bootstrapped using the symmetries of the theory. And this is done by solving this type of equation, which involves the coproduct. And since we have seen that for different choices of Cartan Weyl basis, the coproduct is related by the twist, in fact, the same holds for the S matrices. So this is the S matrix for the Cartan Weyl basis that I denoted with prime, and this is the S matrix with the original Cartan Weyl basis. So the twist also appears at the level of the S matrix. So for instance, this S matrix could be the S matrix associated to the distinguished thinking diagram, and this S matrix could then be the one associated to the fully fermionic thinking diagram, and you can construct this one starting from this one by implementing this twist. And you can actually check that both this S and S prime for these two choices of thinking diagram, they satisfy the quantum Yang-Baxter equation. And furthermore, if you do an expansion, then you match the perturbative calculation of the ETH deformation. So this is the exact S matrix, but you can also start from your ETH deformation and make a perturbative calculation of the S matrix. And because you expect ETH deformation to correspond to a quantum group deformation, a Q deformation, you should have a matching, and indeed you have this matching. Good. So now let me come to the conclusions and the open problems. So we have seen that an effective way to generate new integrable theories is to deform already known one while preserving integrability. So for instance, going from the HS5 cross S5 superstring to its ETH deformed version. And indeed, a particular type of such deformation promotes the symmetry algebra to quantum groups. So this is called the Q deformations. Here I focused on the ETH deformation where Q is real, but you also have lambda deformations where Q is a phase. So this is the realization at the level of the sigma model. Now we also have seen that because you have different Cartan Weyl bases for superalgebras, the ETH deformations are actually not unique, and there is only one type of ETH deformation that is a string theory, and the exact S matrix are matrices from which you can then compute physical observables are related by a twist. So there are some open problems that still need to be solved. So now that we know that the S matrices are related by this twist, it will also be interesting to look what will be the effect of this twist actually at the level of the observables. So for instance, the spectrum of the theory. Then it would be also good to better understand the Weyl anomaly in ETH deformations. So the fact that they are not string theory, why is that so? And the connection between the lambda and ETH deformations. So both of them are Q deformations. And when you put the fermions to 0, they're actually related by what is called Poisson-Lie duality. And it's an open problem whether this carries on to the superstring case. And also, since you have this different eta deformation, does it still work? You have this different eta deformation. The question is whether you also have different lambda deformations. And the broader question is to understand Q deformations in the context of holography. So you have the ADS5 cross S5 that admits this CFT dual n equal 4 super Young-Mills. Now you have deformed the ADS part of the duality, and you can ask yourself what happens to the CFT side. Can you also deform this and have some duality between these two deformed theories? So that's the end of this talk. Thank you for your attention, and also a special thanks to my PhD supervisor and also my collaborators, some of whom are in this room.
Well, thanks a lot. Any questions or comments?
So I have a question about this twist of
Yes.
the S matrix.
Yes.
Because in other similar setups, in fact, for this one, there are other twists that appear sometimes. And it turns out when you diagonalize this matrix to write some better access equations, this twist sort of factors out, and you find out that actually up to redefining some identification of the leg size of the worship, you basically just have an equivalent description. So do you, well, first is whether you check what happens when you diagonalize this matrix for this twist, and the second question is whether you expect to really need a different description of the same spectrum or really a completely different model.
So no, I did not check what happens when you diagonalize. And so the twists that you are talking about, are they continuous or discrete?
Well, it's discrete. Usually the one that takes you from the so-called string frame, which is the worship description, to the string chain frame, which is the integrable n-4 super Young-Mills string chain description. But in that case, it's exactly the same model, just described in two different ways.
Yes, yes. So I cannot really answer because I don't know what will really happen when you diagonalize and when you start applying the integrability techniques. I don't know really whether this twist will lead to this theory or not. I don't know yet.
All right, more questions or comments? I actually have many questions, but let me restrict myself to two of them. So you've shown to us, but maybe you can show again this formula, how the S matrix changes, that one by a twist when you change the Cartan-Seid algebra. But I haven't quite understood. So right, if you take those two different Cartan-Seid algebras, that's S and S prime, but can one now compute this S or S prime?
Sorry.
And you don't show them to us just because you think we're going to be scared, or what's right? Because you're saying what happens if you change something, but what is S and what is S prime?
So indeed, this S, you can actually use the symmetries and compute it exactly. So for this has been done, so at some point there were some references. So this has been done actually by Beisert and Korotev in 2008, and in this recent paper with Van Tongeren and Zimmerman, I computed the S matrix both by implementing this twist and also by bootstrapping from the symmetries, and the two formalism agree. So I don't show them to you because already, so they are very complicated. They are parameterized by 10 functions that are quite complicated, so they would fill a slide, and I'm not sure you would take something home from it. But I mean, they are explicitly written down, they exist. It's just that I didn't.
So that's as I suspected, you're just being gentle, right? Okay. Then I have another question, which is more philosophical, but maybe it shows that I haven't understood much. So you said we focus on integrability.
Yes.
Right? And usually when we're talking about string theory, we focus on conformal field theory. right? But integrability,
Yes.
does it mean that your theory is not conformal? Does it flow somewhere? Does it have a non-vanishing beta function, right? When you do ETH deformation,
Yes.
the theory on the gold sheet remains conformal?
No. So when I was saying that the ETH deformation is can be a string theory or not, I meant it is. So in one case it will be a CFT on the world sheet, but in the other cases you will no longer have the CFT on the world sheet. While invariance will be broken.
Okay, so that's one case, right? That the
Yes.
one which was green.
Yes, exactly.
And then all the other cases
In this green case, you have a CFT on the world sheet. While invariance is there, all is fine.
And how do you control it? Kind of, so you change the symmetry, and what's the computation of the?
To see if it is a string theory. So what you do is that you actually check the supergravity equations of motion. So you start from the action, you expand to quadratic order in the fermions, you extract the background, so metric, B-field, Ramo-Ramo fluxes, you check the supergravity equations of motion. In one case, it is indeed, you can find the background actually solves the supergravity equations of motion, whereas in the other one, the background does not solve the standard supergravity equations of motion. So I add standard because the other will satisfy some generalized version of these supergravity equations.
I'm kind of ignorant. So, but that's the, does it mean that it's in the leading order, the CFT, or does it mean it's going to be exactly CFT, so there will be no corrections?
So I think that for ideas, I mean, for some theories, when you have it at one loop, you have some symmetries or some arguments to say that it will carry over. In this case, I'm not sure you have this argument, so maybe you would have to test it. Yeah, we may want to test it to higher orders.
So it might be CFT.
Yes, but yeah, I don't know. Yeah.
Okay, well, thanks. More questions or comments? Well, if not, thanks again and congratulations.